Welcome to Web Handling. My name is Dave Roisum. In this video we discuss the shells used for live shaft, dead shaft, and cantilevered rollers. The shell is the body of a roller. It has many interrelated functions. The primary function is to minimize beam or gross deflection. Most rollers are sized to a class B or C as defined in the Mechanics of Rollers book. By far the most important geometry here is the outside diameter. While modulus and wall thickness matter, they are so much less influential that it is with little exaggeration to say that in most cases, roller diameter is sized by deflection. In addition to beam deflection, we must also have wall thickness big enough to avoid shell deflection, sometimes called oil canning. Here, the walls at the middle are free to flex, while the ends cannot because they are supported by heads. For the first two criteria, bigger is better. However, bigger is not better due to cost and increase in inertia. Thus, if you size the roller too big, you cost your company money. But if you size the roller too small, you cost your company even more money. The roller surface must be resistant to abrasion and dents, and thus we may have to choose a harder metal such as steel or even coat the roller shell as described in the next module. The roller shell has much influence on roundness, TIR, and balance. Finally, we need to figure out how to attach the roller shell to its head and do so precisely and securely. There are three common options for a shell's materials, each of which has many variations. Aluminum is mostly confined to idler rollers, as are composites. Iron and steel and their many different alloys are the workhorses of process rollers and are also used on many idler rollers. Stock tubing may not always be good enough for web handling application. Often the outside and ends must be machined. On critical process rollers, the inside may also need to be machined. The geometries are as varied as the alloys. Casting, or continuous casting, is sometimes used, but extrusions are much more common. Centrifugally cast rollers have precise walls and can have outer surface harder than the core, such as in chilled iron rollers. However, rollers such as these often tend to be called drums because they may be much larger than most rollers. Seamed pipe is sometimes used instead of extrusion, but they tend to not be anywhere near so geometrically precise. Finally, composites are a mix of carbon or glass fibers in an epoxy matrix and can be made in a number of different ways to customize strength and modulus in different orientation for different application needs. Finally, the shell must be attached to the head in some fashion. Bolting, bonding, and press fits are all in common use. Just as with any web handling or converting component, there are design and maintenance challenges. The first is sizing that is well described in Chapter 3 of my book. However, merely being big enough may not be good enough. Rollers need to be geometrically precise to about the thickness of a human hair, plus or minus one order of magnitude. Some design choices are inherently easier to get precise than others. Imbalance can be a challenge at higher speeds, such as common in film, metal, and especially paper. Not only must there be provision for static or dynamic balancing, but the design must be such that it is balanceable using reasonable balancing weights. Some precision rollers can be put out of balance with a piece of tape. Finally, attachment to the head has many issues related to stiffness, strength, serviceability, and reliability. Some complicated designs may need to pass fluids or electricity through the rollers. Thank you so very much for watching this module in my Plant Practical series. Please stay tuned for the next module where we discuss roller surface coating options.